Hello there, young students of chemistry. This is a recording to summarize what you learned in your iodine clock reaction lab regarding reaction rates. So collision theory is the theory that tells us just what the words say. I mean, it says collision theory. What they're telling us is that, hey, in order for reactions to occur, particles must collide. And anything that is going to change the number of collisions per second or change the force of the collisions is going to change the reaction rate. So in your lab, you were looking at the relationship between temperature and reaction rate as well as concentration and reaction rate. There's one other thing that we should consider, and that is that when particles collide, they must collide with enough energy to make that reaction occurs. And that is what we call activation energy. You can see that we abbreviate that energy E sub A, so that's energy of activation. And when the particles collide with enough activation energy, they still have to collide in the proper manner. The right parts of the particles must bump into each other. So because of that, we can kind of predict how a rate is going to change, but we're not always right on because those collisions that occur might not be what we call effective collisions. Effective collisions are collisions where the particles are colliding with a proper orientation and they are colliding with enough activation energy. And you know this about activation energy if you've considered even just a match. You know, the match inside the box has all of the chemicals on it to create a fire, but it doesn't do that because you need to strike the match. And striking the match gives those reactants some activation energy in order to make that reaction go. When I talk about orientation, this is what I mean. What they're showing here is a reaction between N2O and nitrogen monoxide. So nitrogen dioxide plus nitrogen monoxide, the right parts bump into each other and we get nitrogen gas and nitrogen dioxide gas. So what this little slide is showing you is that if the oxygen bumps into the nitrogen, then oxygen will dislodge from the N2, the dinitrogen monoxide, and lodge to the nitrogen monoxide, right? But if the oxygen particles bump into each other, there's no reaction. And if the nitrogen parts of the molecules bump into each other, there is also no reaction. Those particles just collide and bump off of each other. So in order for this reaction to go, the dinitrogen monoxide must collide with the nitrogen monoxide with enough energy and in such a way that the oxygen part of this molecule bumps into the nitrogen part of the second molecule. And that's what we mean by proper orientation. So reaction rates. We know that we can change the rate of reaction by changing the number of collisions per second. Temperature, much like pressure, affects the reaction rate in two ways. If we increase temperature, the particles are increasing their speed, and when they increase their speed, they're going to have more collisions per second. Due to speed of the particles, which is going to increase reaction rate. So an increase in temperature causes an increase in rate. The other thing is, if they're increasing in temperature, that means that when the collisions occur, the collisions are more forceful collisions. And therefore, temperature is going to affect the rate of reaction in two different ways. Concentration affects the rate of reaction, and you saw in your lab with your iodine clock reaction that increasing concentration, remember those brackets mean molar concentration, increasing concentration causes an increase in the rate. And that is because there are more collisions per second. There's more particles present. Therefore, it's more likely those particles are going to bump into each other. You know this. If you're in the hallways during class change, it is much more likely that you will collide with someone than if you're in the hallway going to bathroom during instructional hours, during class time. Much less likely you're going to bump into somebody. Surface area also affects reaction rate. So the greater the surface area increases the rate of reaction. And it's very easy to change the surface area because we just change the particle size. So we grind a substance into much smaller particles. I've had the opportunity to be in many factories in my lifetime, and one of the cool things that I was in one time was a place where they milled wood. I love the smell of wood like that. But I noticed that their electrical boxes, like their light switches, were really strange. They were completely covered. And I learned later that the reason they have to really protect the electrical circuits is because in the wood shop where they're grinding this wood into boards, they get really fine particulate pieces of wood, and one little spark from turning on the light might set that place on fire. My ex-husband's father was also a Green Beret, and one of the things he told me that his unit did one time was they put some fans to a building and filled it with flour. So they just like dumped some flour behind these fans and filled a building with flour and then lit that on fire, and it caused the building to implode. So really small particles react a lot faster than large particles. I don't know if you remember your brass penny lab, but the zinc powder that we were using there was really fine, and that would catch fire just by you rubbing it with a paper towel, whereas you could take a piece of zinc, a sheet of zinc or any kind of piece, you could rub that all day long with a paper towel and it is not going to catch fire. So surface area, in smaller surface areas, smaller particles are going to have a greater rate of reaction because they have a greater surface area. There's more places along the edges for the particles to bump into each other. So if you think about like a cube of something, if we grind that into smaller pieces, I'm going to draw that in red, right? So we break it up, put it into a mortar and pestle, right? You've changed the surface area. When it's not ground up, the only surface area where particles can bump into each other are the very outer surface. However, the red lines would indicate new places where particles could bump into each other, because of course that would fall apart. I can't draw that falling apart. Sorry. And we know a catalyst. You learned in biology that catalysts speed up a reaction. And catalysts speed up a reaction by doing a couple of things. They lower the activation energy, and they provide a meeting place for the reactants. You'll see this energy diagram that has the energy and then the reaction progress. Sometimes you'll see time. But you have the energy of the reactants here and the energy of the products here, right? And what they're showing is the activation energy. So this value here, from the energy that the reactants already have to the top of this hump, is the activation energy. Excuse me. And then this difference here between the energy of the reactants and the energy of the products, this is the enthalpy of reaction, the heat of reaction. If we have a reaction where there's a catalyst, what you'll see is that this hump is lower. but it does not change the overall energy of the reactants or the products. Okay, so there's just a little summary of collision theory and how we can speed up the rate of reaction.